Okay, thank you to be here for the lecture of today. Now, in these two lectures, two final lectures, I will introduce the concept of nonlinear dynamical systems. Until now, we have seen everything in form of linear systems, which do you remember the basic concept was, even though I didn't tell you much, but the superposition principle. This means we have two causes which generate an effect, but we can consider nevertheless separately one cause with an effect, another cause separately with a second effect, and then we can add the two effects, and we have exactly the effect which we had when we apply both together. Do you remember I told you at the beginning this, not formally, but do you remember free answer, forced answer? No? We have two causes. Input, first cause. The second cause is the first cause is the input or the initial condition in terms of mathematical aspects, and the second cause is the external input. This just to remember. And mathematically, this is reflected by differential equations in which we don't have a product, for instance, between two variables. We don't have a product between state variables, excuse me, state variables. We don't have a product between input and state variable, or the state variable, also the input, as linear combination. This means linear combination means, I don't know if you remember in math, no function, no state square, not input square. This is a little bit the idea. Of course, we have also in a formal definition, and we can prove if in the system, dynamical system is linear or not, but I told you a little bit with this criteria, which nevertheless are good criteria, to recognize if the system is linear or not linear. Basically, it's linear if and only if states and input, they appear in the model in a linear combination. This means a constant multiply x1 plus another constant multiply x2 plus b multiply u, a linear combination. Of course, I don't have time to repeat. I also had the time to repeat exactly the definition of linear combination, but anyway, you know from math, but it's intuitive. No products, no square, linear combination, and reflect the physical concept of a superposition principle. Okay, if the superposition principle does not work, it mathematically, as I told you, we can recognize because of the presence of product between states, as I told you until now, and not linear, let me say, connections between the states and the input. We are in the presence of nonlinear system, or better to say, nonlinear dynamical system. Here, we add the word dynamical because we are working with differential equations, because we want to apply math 1, math 2 in the engineer field. But nonlinearity is the more general as linearity. No? This works also, if you remember in high school, in algebraic systems, not dynamical. No? If you have, for instance, do you remember, 1 equal x plus y, and the second equation is 0 equal x plus 2y. Do you remember in high school, you have to find x and y. The linearity can be seen also in this algebraic, not dynamical, because we don't have the derivative. If the system is linear, we can have one solution, we have an infinite solution, we have no solutions. We have some criteria which we can really determine if there is a solution or not. How many? I don't know if you remember. No, if you have just to understand, two lines, if they are parallel, they don't have solution, they don't meet. Think about your high school. I don't have time to repeat. But if you have, for instance, the equation like arctangent of x, which multiply y equal 3, and the second equation is x squared plus y, no, God knows how many solutions you have. And it could be real, could be not. It's extremely complex. Also, in algebraic frame, if the system is dynamic, of course, here it's a little bit more complicated because to find the solution, we have to know a little bit the theory, which I did together, which I repeated, of the differential equation. But what happens in nonlinear systems? As in algebraic system, the teacher told you for some classes of algebraic system, we can know in advance how many, but not always is possible. Not always is possible to calculate. In general, we cannot. Also here, we don't have really always methods to calculate exactly the solution. Could be more than one. In linear, as if you remember, could be one generally, but could be no one if you think a two-line parallel, or it could be infinite. If it is two-line, a base is one. I don't know if you understand what I intend. Think about 1 equals x plus y, and the second equation, system with 2 equals 2x plus 2y. At the same, because I multiply just the first equation by 2. This means if the equations are depending, you remember this concept here, depend. Forget this, we are here for dynamical system. Just to understand, in linear case, we can find some recipe, we can find some criteria in which we can say something more. If the system is non-linear, we cannot say in general anything. The same concept we have in dynamical systems. If the system is non-linear, very often, the most of the case, we don't have the analytical solution. We don't have, believe me. And in this sense, we have to be happy if somehow we can decide if the system is stable, if the system is not stable, if some points, now the concept of the point I will tell you in 1 second, if in some points the system is stable or not. Why I'm introducing the concept of some points? The reason is, in nonlinear systems, we don't have, as I told you last time, the concept of the eigenvalues. Remember last time I told you a lot about the eigenvalues. To conclude the chapter of the linear system, I introduced this at the beginning a little bit, the exponential, the coefficient of the exponential function as the eigenvalue of the associated matrix and so on. We don't have this concept here. This means very often it's not easy to find an analytical solution. There is method and so on, but for particular classes of different nonlinear differential equations, very often we are able to say if in particular points, the name of this point, equilibrium points, the system is stable or not. And very often we try to calculate control strategy to remain around these equilibrium points, or why not to generate a new equilibrium point to control the system. The idea for engineer, or at least the goal should be for not only this, but the most important goal is to control the system. And very often we are happy just saying that the system is stable or not stable, or stabilize a set of points and a trajectory, and to work around this. Okay, let me start with some mathematical concepts. I think it is better to show you at the beginning something related to the equilibrium points. Yeah. Before switching on the lateral camera, let me open the presentation. At the end of the lecture, we'll upload very shortly a couple of slides, but I will upload everything. Because it could be now, at the beginning, the idea was to tell you directly on control, but let me tell you about this. It can help to understand the rest better. Okay. Right. I will upload it later. Share very quickly. Look at this. Look at this line. Competitive Lotka-Volterra equations. Look at these two equations in the middle. I don't want to be really boring, but you can see directly that the derivative of x with respect to the time equal alpha multiply x. Until here, I don't see any nonlinearity, no? And a constant which multiply the states. Then we have minus beta, another constant. Look here, x multiply y, in which x is in state because we have the derivative of x with respect to the time. You remember, we recognize the state mathematically if they appear in a differential form. Because you remember, I told you the states reflect the energy. And if you remember in high school or here in some courses, the energy, the kernel of the energy, its variation. I don't know if you, the potential energy of these glasses with respect to the table is zero because no variation is possible. But with respect to the ground, yeah, just colloquially. This means this is reflected. The concept of this keyword reflection is extremely important in our field because we have a reality to be described. Yeah, description, but it's reflected. It is more interesting, this word, in the mathematical expression. Alice, you understand what they say? Yeah, a little bit. The concept of reflect. The derivative reflects the variation. Yeah, this is easy to see. In this case, over time, no, over time. Dynamical in the sense with respect to the time. I move over time. I held a lecture about the time. I don't know if you received my invitation in 10 minutes theology. My study, I forgot this semester probably to invite. I don't remember. You don't remember, okay. Y is also another state we can see from this derivative, and this means that x multiply y states a nonlinearity because if you apply the superposition principle here, it doesn't work. Free answer, fourth answer, even though we don't have an input in this form here, but you can believe me in this sense. Yeah. This is the system which is nonlinear. I don't want to now to go in depth on this very famous model, again, Lotka-Volterra equations. Basically, is the model which is used in competition to analyze competitive model. It's used in economics, it's used in virology. We will see later an example with the COVID. We will use something similar, a little bit simplified, but it's very famous also model. I don't want to go in depth because the goal is to show you the concept of equilibrium points in order to say that in a nonlinear system, we cannot say that the system is stable or not stable. These two categories are unstable. Not stable in the sense, excuse me, we cannot say that the system is, remember, asymptotically stable, first category. The second category was stable, we have seen last time in detail. The third one, unstable. We cannot say anything in general if the system in general is something related to the stability. We can characterize just some points. This means if the points are, let me say, better to say, if the neighborhood, the point, around the point, the vicinity of the point is stable or not stable. This is related to the concept that in nonlinear systems, the characteristics or the stability characteristic is not a global characteristic. We cannot say that a system is stable, dot. We can say for linear system, could be time variant, time invariant. I told you a little bit about that, but go a little bit ahead. We can say just if some points around this particular point, which we call equilibrium point, we have the stability or we don't have the stability. More complex is also to determine how large is the point of, is the region, excuse me, of the stability around these points. But let me go from the beginning. Again, we can define some equilibrium points, if they exist, of course. In linear system, we have just one equilibrium point, and this is 0. Therefore, we can say if the system in general is asymptotically stable, stable, or unstable, because we have just one point in the domain of the linear system as an equilibrium point. Here, look. Assuming this is in a definition, which makes sense in the sense any definition should reflect the concept which we want to express. Equilibrium points are the points which we don't have changes. Means if I am here, I remain here. This is what we want to reflect. It is reflected by these two conditions in our particular case. We have two states, two energy. This means, is the table a set of equilibrium point? It is. Remain. The energy remain in all points, just to understand what it entails. No changes in potential energy. Is this point an equilibrium point? No. It's just to do, excuse me, this trivialization, but allow a little bit to reflect the concept in math, extremely important in our field, in system theory. Now, assuming this definition as definition of equilibrium points, this means practically that no energy changes for X, no energy changes for Y. Before going ahead, nevertheless, I would like just say you one thing about this model here, because otherwise too few, even though for us it's not important, but X represent the dynamics of the prey, Y represent the dynamic of the predators. We can a little bit understand if delta is 0, for instance, this means no contact between X and Y. This means this product here does not work in the dynamics. The product stays semiotically, you know the word semiotically, semiotic? The meaning of the sign, the meaning of the symbols, means that X could represent the rabbits, the number of the rabbits, we change over time. Y could represent the number of the foxes. This means if this product is not active, because delta is 0, delta represents a barrier and a wall between, we have this room, in this part you have foxes, the other part you have rabbits, and we have a wall. They cannot communicate, they don't have interaction. What happens to the foxes? I don't know if you remember, we have seen many times, the differential equation, the derivative of y with respect to the time equals minus gamma multiply y with gamma positive. We can see here all constants are positive, means that the foxes will extinguish. Because the solution of this equation, if this element is not present, is the initial condition y0, which is the number of foxes at time when I start to observe, to simulate, to observe my ecosystem. I don't know what you can say. Don't trust me about the nomenclature. Starting from y0, I don't know, 100 foxes, going to 0 in accordance to the model exponentially. About that we can discuss, but I'm not here to do a lecture on this biological system, because exponentially is in a mathematical model. Basically, I have 100 foxes. Tomorrow, if they don't catch the rabbits, we will be 99 or 98. This means we change not exponentially, but something like. But this is really a little bit more complex. I don't have time to. But it's interesting in order to show you that in my lab, we do also some kind of work. Modeling of everything and control of everything. And through this discourse, at least I would like to give you the feeling that this field, this topics are important for everybody, believe me, because we can start thinking what is the meaning of modeling, why math is important, in the sense we can find some interesting application, even though with approximation, even though with simplification. Yeah, also here, no? If they don't meet, not only delta is zero, but also beta is zero. Now we can see this symmetry in the equation. And this dx with respect to the t equal alpha x, this means that the rabbits, alpha is positive, will grow up, the population. The people say, but in this room, how we can grow up without food? How we can grow up without, grow up means also enough room. In fact, this model is in a simplification. We did include the constraint in terms of food. We did include the constraint in terms of room. This means infinite room, infinite food. We have also some interesting analysis in which we feed with food the foxes, and we will see really mathematically how they are less aggressive with respect to the rabbits. Believe me, it's interesting. If you want to work on this field, I can help you in this sense. We received also an award as the best paper in the conference with it is also in Loifana, Katerina Benz, the student from sustainability. He did a thesis, bachelor thesis, on an equilibrium situation fisher in a lake. That's interesting. Okay. Equilibrium point. When the number of rabbits doesn't change, when the number of predators doesn't change. This means we have an equilibrium point. One rabbit will, the foxy will get the rabbit, but the rabbit reproduces it immediately. This ideally, of course, if you look in some paper of my students, they oscillate around this point practically. Because equilibrium means, again, if they communicate, because if they don't communicate, we don't have equilibrium points. I mean, equilibrium point for the predators, yes, because it goes to zero. But the rabbit, this means it's not an equilibrium point in general. If you want this equilibrium point for the we will see it's not in the sense of the definition. We will extinguish the foxes, and the rabbit will be infinite, theoretically. We don't want this. We want to preserve both. In a normal ecosystem, the species should be able to survive in the sense. Look, with this mathematical condition, if apply exactly the definition to my two equations, I have a zero here instead of the derivative of x, zero here instead of the derivative of y. This means now we have to solve this algebraic equation in terms of x and y. We have two equilibrium points. Believe me, I have to accelerate a little bit. One is 0, 0. This is intuitive, because if you don't have rabbits, if you don't have foxes, the system, the ecosystem, let me say, I don't know if we say ecosystem, but it doesn't matter, is in equilibrium because no changes, no rabbits, no. It's the trivial, we say, equilibrium point. But we have also more interesting equilibrium point, which is depend of the parameter alpha, beta, gamma, delta. I don't have time to explain the importance of these parameters, but these parameters really characterize physically the structure of the system which we are considering. They depend. Sometimes it's very difficult to be identified. Depends on many things. But in any case, we can see that exists an equilibrium point, x equal alpha divided beta and gamma equal gamma divided delta, in which these two spaces, they are in equilibrium. We will see, I don't have time, but if you want to do something in the bachelor thesis, that this point is characterized by oscillations, practically. Not only practically, also mathematically, but mathematically in the neighborhood, close to this. This means the rabbit will increase. If the rabbit will increase, we will increase also the foxes because they have more food. And then the rabbit will decrease. And if the rabbit decrease, we will decrease also the foxes because they don't have food, and the rabbit will increase, just colloquially explained. This oscillation, we can understand that a little bit intuitively. Mathematically, we can see. It's a shape, not analytically. You remember last time also, I calculate the oscillation many times in this course. When we have in linear cases, oscillating solutions. Here it's not possible, at least for this kind of equations, Volterra, we don't have an analytical solution. I cannot see mathematically exponential, arcotangent, it doesn't matter what. I don't have, it's not possible. At least until now, we didn't find any analytical solution. We can simulate numerically with Simulink, MATLAB, and so on. And we simulate this oscillation around this point here. Around. The word around is extremely important because how large is this oscillating equilibrium point is a big problem in control system theory. Because if you go far away, you fell down at 0, or you go infinite for rabbits, for this model here, and 0. And I think infinite also for predators, excuse me. Anyway, 1 second, and then we will start with an example. Look at this theorem here. It's the theorem which allows to classify the equilibrium points. What is the meaning of the word classify? I have seen that we have here 2 equilibrium points, 0, 0, and alpha divided beta, gamma divided delta. This theorem here states how we can say if the point x0, x0 is in this case 0, 0, and another x0 is this one, is stable or asymptotically stable or unstable. Really, we can see that we have just 2 categories here. Asymptotically stable means exponentially stable. We have a difference. Exponentially means it's going to 0 as an exponential form. Asymptotically, very often we say exponentially, but go to 0, 1 divided t squared is going to 0, but not asymptotically. Anyway, at this moment, I don't want to be so precise. For us, exponentially equals asymptotically, it makes sense, because go asymptotically to 0. But asymptotically is wider. 1 divided t squared or 1 divided t go to 0, not asymptotically. No, it's not, excuse me, but not exponentially. 1 divided t is going to 0 for t larger, but not exponential. You understand what I intend. But exponentially, in any case, it is asymptotically. We say that in this case, x0, the mathematicians say 0. No? Our 0 is more general, could be the 0, but could be also as 0. 0 in math is a reference point. It's our candidate point. It's a little bit strange, but the mathematicians work always with 0. But our x0 could be this one, exactly, concretely 0, 0, but could be also this here. The mathematicians say this is our 0. But I understand the mathematician because it is just a definition. But anyway, we have this condition, this category, I would like to say, and unstable. We cannot say if the system is, do you remember, stable with oscillation. This is a little bit more the sense complicated to at least it's not included in this theorem here. We can see here, that it depends on the eigenvalues of the Jacobian matrix. We can see that it's all eigenvalues are negative. We have the exponentially stable equilibrium point is exactly as in a linear system. Why that? Because we are calculating, I don't know if you remember the Jacobian format. The Jacobian, which is the matrix, why I speak about the matrix, because we have a system with 2 variables of the derivative, or the partial derivative of the system. This means it's like a Taylor approximation, no? You probably math, you remember, around the point which we want to analyze. This means yeah, the Jacobian states its Taylor approximation around the point x0, in this case 0, and analyzing basically the linear or the linearized system, we can say if it's stable in accordance, excuse me, asymptotically stable, exponentially stable in accordance of the eigenvalue. Exponentially is clear because in linear system, we have the exponential stability, which equals the asymptotic in this sense. But asymptotically is more large in this sense. Or we can see here, unstable if at least one eigenvalue we have seen. Basically, this reflects these two criteria, the linearization. And what we learned in math, what we learned also here in the context of linear system. Look, all rest of the situation, no conclusion. This means if we have 1, 0, lambda equals 0, or more than 1, we cannot conclude anything. It's very often to look if I have oscillations, or in general, to remember when we have complex, we have seen last time, eigenvalues. If we have complex eigenvalues, we have the real part is 0. Yeah. Real part, no? I forgot to say, but it's the real part we determine, you remember last time in the linear system, but it's clearly written. In this case, we cannot conclude anything. This means could be stable, could be unstable, could be persistent oscillations. If we are able to calculate the solution, we can see analytically. Very often, we are not able. This means we have to simulate. This theorem says just in these two conditions. The rest, no conclusion. In German, is keine Aussage. No? So, I don't want to go ahead here with the calculations of the Jacobian because it's not exactly, but just scrolling down, we can see here, I will upload. Nevertheless, I can calculate the general Jacobian, and then I will calculate Jacobian means, I don't know if you did in math too, I think so. The matrix of the partial derivative. But Taylor, you know, as a concept, no? The approximation of a nonlinear function, what? Not a nonlinear function around a point. It's exactly what I'm doing. Using the Taylor expansion, no? the derivative. Here it's quite similar. We use, nevertheless, just the first derivative. But why we are speaking about the matrix? Because we have a system. We don't have any function, a scalar function. We have a system relatively complex. This just to give you a feeling. I don't want to go in depth on this. And then we can see here the general Jacobian, in which we can see this element here is the derivative of this expression here with respect to x. This element here is the derivative of this expression here with respect to y. In math we are stuck. No? We are strong. And here in the second row, we have the same the derivative of this expression with respect to x. We can see delta y. And then the derivative of this expression here with respect to y is here. No? We can see that is delta x minus gamma. Now we can calculate this at our candidate equilibrium point, 0, 0. And the eigenvalue of this matrix here, you remember, last time I was really boring on this equation. You remember? We can calculate the eigenvalue, which is here, of this matrix here. We can see that we have an eigenvalue is positive. Oh, interesting. If I don't have rabbits, if I don't have predators, the equilibrium point 0, 0 is unstable. Strange, because if I don't have rabbits, if I don't have predators, how can? This I would like to tell you. It is possible mathematically because don't have to forget that we are working mathematically. Meaning, the approximation with Taylor works in the surrounding, in neighborhood, around, close to. Do you remember the concept? X minus x0, no? This means mathematically, if I have 0,10 up to minus 3 rabbits, that practically doesn't mean anything. If I have 10 up to minus 6 rabbit, this doesn't mean anything. If I have half rabbit, that's how the rabbit will grow up, but mathematically. Of course, we can see here the limit of this model because how half rabbit can be reproduced? Just mathematically, just in the abstract sense. If you want to have a model a little bit more interesting and more connected with the reality, we have to distinguish between male and female rabbits. Otherwise, they reproduce. This is just in a mathematical abstract, in saying the essence of the rabbit we will reproduce. This is extremely interesting to understand these discrepancies between possible discrepancies between math and the reality which we want to describe, I can do the same for the other equilibrium point, but we will see here if I calculate the eigenvalues, we have eigenvalue with real part 0, two different eigenvalues. Remember last time I insisted a lot when they are equal, they are no conclusions. We have to calculate analytically, we are not able, we have to simulate. We will see that around this point, we have oscillation. We can see that we can guess that we had oscillation because this I is J sometimes. So last time I told you J, the imaginary part. But why we cannot say that yeah, because we don't know how large is this equilibrium point. In fact, if you simulate, if you go far away, the solution will diverge, infinite x, infinite y. At the point gamma delta alpha delta, excuse me, gamma delta alpha beta, I think here I inverted. The first coordinate was alpha beta, the second gamma delta. Yeah, okay. In LaTeX, LaTeX, I inverted. At the point, they don't change, they don't oscillate. You remember? The x with respect to the t equals 0, the x with respect to the y equals 0. If you move a little bit, we have oscillation, but we cannot say how large is this oscillation in this sense. We have to check. But we don't know if, in general, if it's stable or not. We have to check. Because it could be, if I move a little bit from this point here, again, alpha, beta, gamma, delta, I invert it here. It could be that it's go far away, because in the theorem, this case here is not reflected. When we have eigenvalue 0, it doesn't matter if 1 or the 2 times 0, no conclusions. Let me now switch on the lateral camera and let me tell you about an interesting system in which we will use another theorem. Again, Lyapunov. But a theorem which we can be used to stabilize, which can be used to generate new equilibrium points, because not necessarily I like the natural equilibrium point, which depend of alpha, beta, delta, gamma, because this element characterize the system. This means I don't like this, I would like to control the system is in another equilibrium point. To do that, I have to put food. I have to manipulate. Look at this equation here. We can see that we have the same equation with two possible inputs. U characterize symbolically our input, uy characterize another symbolic input, one for food for x, assuming that is food. One food of y. of course, with these two inputs, I can change the equilibrium point. I mean, you can imagine that if the fox is satisfied with this food, it could be that they don't catch the rabbits. This could be, we can work on this topic really in the bachelor thesis. No, this is not the topic of the examination, but just to understand at the end of the course makes sense to tell you that the reality very often can be modeled better with nonlinear structures, and to show you how it is important, in my opinion, math, which you learned, it was boring probably. I hope that this lecture is not so boring with math, as math. Okay, we can see that somehow we can include inputs to modify, to change the system, to work with the system. Because I don't want, for instance, that the rabbits will extinguish. Typically, as I told you, is in accordance, in my knowledge, in accordance, the reasonable thing, we don't want that some species will extinguish. Why? Basically, all species they have a right to exist. In fact, there is some law that protecting, I don't know, but makes sense. Why the rabbit, the foxes should distinguish. At least it should be, if I say I don't have nothing against the foxes. Look at this. Now I tell you something interesting. These two equations here, again, reflect this equation here in which I put here alpha equals 0. I called gamma equal R. We will see what is this R here. Instead of X, I have S. Instead of Y, I have I. And I didn't consider both input. I considered just one. I have these two equations. The first equation is just a modification, just putting alpha equals 0. Alpha, I didn't tell you before, represent the reproduction rate of the rabbit. Alex, you know already this?
Kind of. I did have a compliment.
By me.
Oh,
but if it's boring, I go faster. No?
I mean, even if I think it kind of, others say you can get there by just thinking about it, obviously, right? If you have
it's obviously, yeah, it's clear. If you're good in math, it's obvious. This means you're good in math. Yeah, you're good. Please pay attention. I trust a lot the students. Sometimes the problem of the students is they don't trust themselves. Believe me. But no, I'm not speaking about you. Not in general. I noticed that really you have to think that the math is generated by our thinking. This means it's aspects or a topic which can be understood, should be understood. It's more difficult sometimes to understand some religious aspects because they are dogmatic. Something that is generated by our self, because the dogma means that God say us something, we have believe or not believe. This is difficult to understand, probably impossible to understand. They are two different categories. But if I try to explain something, in particular, this does not come from me. This is, look here, this Kermack, McKendrick model, which is used also today in COVID. It's a simplification, but still effective. I mean, can be used in any case. There is also more complex. We can see here, for instance, this. The name is SIR, in accordance with the notation, or we can consider ESIR model, in which we have latency of infected. Anyway, I don't want to go real in depth on this modeling because we are extremely advanced model, but this model is still used. Was one of the first model in the epidemiology. Look, these two equations is basically this one in which we don't have, I mean, alpha is equal to 0. And I would like to explain this. What is S? S is the number we can see here of susceptible people. Susceptible people are the people number, we change over time with this form here, is the people which can be infected. In German, I don't know what is the name, Anfälliger. I mean, potentially infected. Anfälliger, no? So wait, so. But in English, I'm sure that in the paper of Kermat McKenzie, if you look in Wikipedia, you can find this famous model, exactly so. And then they, I don't know if they directly, but we have many variations in which we consider latency, which we consider, I told you here, the equation number 3 is really in a simplification. Let's explain the equation number 2. The equation number 2 is exactly what I told you before without, and I mean, if you look here without, it's exactly what I told you before. This means S represent the prey, I represent the predator. I mean, the infected tries, I would like to say, tries to infect the S, the susceptible, as the foxes try to catch the rabbits. The goal of the infected, the goal of the virus is to infect. But please pay attention. To infect does not mean to destroy. This I would like to, why we have to infect, to destroy. We can demonstrate mathematically also that the goal of the virus is not to destroy the humanity, to disseminate themselves. In fact, in more complex model, we can see that through the mutation, and say what is the mutation, mutatio, they will be weaker and weaker and weaker because they understand, assuming that the virus understand, that they are too strong, they destroy the humanity. And destroying the humanity, they destroy themselves. The nature is working always to preserve themselves. I am not against the vaccination. I'm not against. But we can demonstrate and make sense also biologically, if you think. But in fact, in accordance with my knowledge, the virus will be weaker and weaker and weaker. I don't know, Alex, do you want to add? You are expert, I realize this. You know something. You know, but you know something. Probably better, you know more than me.
During my final semester, there was like it was also about like systems, but not in a mathematical sense. He essentially just gave us like the program he taught himself, the vessel, and we could the project was essentially hey try to simulate something in the project, and he gave us the what we call with as an example, he gave us the calculated the year before he calculated with students also the coronavirus pandemic, the like infected and not infected people. And I think he did the same thing, or like he used to say equation like 100%, I think so. He didn't directly show us, but he showed us, but like it wasn't his main goal to show us like mathematically, like hey, these are the equations. Instead, it's more like I think he just wanted to show us that you can have some not fun, but you can predict.
Yeah, but you realize how it's important to have an idea to understand better what I am explaining now. Because of course we cannot start with the theory of differential equations in the final semester. That doesn't make sense because you did in DMAT 1, you did DMAT 2, and then also some physics knowledge in other courses can help to understand a little bit superposition principle, something like that. No? Okay, but nice.
Like common sense, right? Obviously, like
It's in common sense, yeah, of course, it's intuitive. And the second equation is exactly what I tried to explain before with this possible equilibrium points, no? Possible equilibrium. But about the equilibrium point, I don't want to go in depth here. We can calculate, nevertheless. If you have time at home, you can calculate the equilibrium point. The equation number 3 is the real simplification, which we say R. Then I will tell you later about the constant R, the constant A, and the meaning of the excuse me, of the input UV. Is clearly the infected people. I told you what is R? People who died or recovered people. This is sure is a little bit in simplification in the sense, no? Because we assume that once you be infected, we have two possibilities: you recover or you died. In both cases, we say recovered. But of course, it's a strong simplification. All the models which consider more compartments, we say compartment instead of states, more states. Do you remember? I told you that to recognize the state is enough mathematics to look at the derivative. We have three states because we have three dynamics, if you want. But of course, in this kind of model, if you look in Wikipedia, we have more than three because we can consider something which is appear susceptible, but they are already infected. This latency concept, no? Latency. Alex, if you want to go in depth, we have a bachelor thesis on this, no? Do follow you. But nevertheless, in the context of, because to study means to be able to apply the knowledge everywhere. Not necessarily an engineer should, we are not here to do education for working directly. We are here to build your mind. This means the knowledge should be, it doesn't matter if it's an economical system, an electrical system, mechanical system, production system, biological system. You are able to apply your knowledge, your thinking in every field. At least this is my concept. And believe me, this helped me a lot in my life for the work. Because if you are flexible to change, to apply your knowledge in different fields, anyway, you can understand that you are stronger than just selecting. And this field allows. Of course, this is a strong simplification in the sense. What about UV? UV, as I told you before here, in the case of rabbits and foxes, could be represented by food, for example. Here, in the COVID model, again, look in if you want in Wikipedia at home on this. There is a page dedicated to this SIR, and I think some variation and so on. But this is the name of this. Again, this McHenry, let me say Kerma McHenry to be precise. This input here represent the number of people. Here, please pay attention. The variation of this variation in terms of number of susceptible people over time. Basically, this means the unit here is people. People is dimensionless, a number. Divided time, day, typically day, no? Each day we read in the newspaper how many people is susceptible, how many people is infected. Here is the number of people which we can or we should vaccinate per day in order to obtain the goal. Which goal? An equilibrium point which we want. What is the equilibrium point? Could be 0 infected, but not necessarily. Ideally, 0 infected, and a number of susceptible people, as small as possible, but typically not 0. Why that? Because not all people should be or must be vaccinated. I mean, I didn't get the vaccination for physical reasons. I received a certification of my doctor, let me say. Yeah. We say, I cannot be vaccinated for immunity reasons. This is in a funny situation. At home, we vaccinate everybody. They will get COVID, me no. But this does not mean, please pay attention. I'm not against, please pay attention. I'm not against. No, no. But please, I would like to explain because now everybody can look at this video. I'm not against the vaccination. Otherwise, I mean, my family, I wanted it, but I am ill in an immunity illness, and this protected me. This is the reason. And in my case, the physician says, in your case, could be more dangerous to vaccinate than to get COVID. This was the reason. And he certificated that. But I vaccinate my family because I have at home my mother, the mother of Ellen, in any case. But this is plain because my immunity system is in particular, since I have other illness connected with the immunity system, immunitary system. But it's a little bit, it seems to be a paradox, but can be explained by my immunitary system is different with respect to the other one. This means the physician say, please, in your case, I don't suggest, because it could be more dangerous this than to get COVID. But paradoxically, I did, paradoxically, makes sense in this context. I didn't get COVID, the whole family was, or at least the doctor says, we cannot say if you, because I didn't check, probably I had, but without symptoms. But again, I would like to, for the people who is looking at my YouTube, I'm not against, no? I'm not against. This is in particular situation. No? The same as I told you, we can mathematically demonstrate that the virus will weaken and weaken and weaker. This is also known in biology. This can be seen mathematically, but I don't want to say that we don't need the vaccination. Far away from my thinking. But there is cases which it's more dangerous to, so told me the doctor. In fact, also here in this model, we will see in a few minutes, that practically we didn't fix the susceptible to zero. Ideally, infected zero, susceptible to zero. We don't have any problems. If the goal, if we try to calculate an UV, which represents the number of people which have to vaccinate to obtain some equilibrium points, in particular, the ideal equilibrium point is infected zero and susceptible zero. This means the equilibrium point, no problem. COVID is destroyed, doesn't exist. But we will see also in these mathematical calculations, which came from literature, we didn't fix zero. Why that? Because it's not possible. My case is an example. The physician say, I don't want to suggest. You can do, but because you have this illness, please don't do it. If you get COVID, we will see, but don't do it. In fact, we know that not everybody should be vaccinated. This is known. This means also here we will see that we fix the level, of course, of a susceptible people, but as small as possible. And this reflects exactly people who is more dangerous, I suppose, to be vaccinated. But it seems to be that, Alex, you know more than me on this, or? But you follow the polemic between vaccination and not vaccination. Eh? You follow. Did you get the vaccination? Yes.
Yes, but very different. Back then, or it will be easier. I know. If I get back to that, like I trusted the experts, yeah, that would be fine. Now it's more like, I think, because for a lot of vaccinations, the risk, sometimes you get like, what we call it, I don't even know the German word.
In English?
Right now, I don't know the German or the English word. Goes by the Nebenwirkungen.
Side effect. Side effect. Yeah, I think this could be represented with this word.
I don't need it. Fine. I just had this discussion several times with like people at work because
You're working parallelly.
yeah.
Now you understand why I'm doing the YouTube. No, I hope that you can profit also from this.
Yeah.
Makes sense, huh? Even though the side effect that the people doesn't come here. That's a side effect, right? But anyway, I think the positive effect is more because I worked also when I was young. I really I desired to have a material more consistent, more which reflect more again reflect more the lecture. Yeah, let me go ahead a little bit, and then we fix a little bit the yeah. We can see with this minus. Why the minus? The meaning is clear because increase the number of vaccinated people. I will give you a negative contribution to the variation. I mean, we decrease the S. No, this means the minus reduce the derivative. No? I don't know if it's clear. This yeah. What about the constant, which is extremely important? No? R is the infection rate. A, which is here and it is here, is the remove rate of infected. We can see in any case 1 divided or that time up to -1 time. The time typically is calculated because we produce in a couple of publications more than two. I mean some publications, and we simulate, we validate our model, which is not this one but starting from this one with different compartments, mean more than 3 states. The interaction in between a little bit more complicated. But we validate with real data, and the data is per day. Basically, each day at that time, we copied let me say, the data from the newspaper, and then we simulate how many people, the idea is to calculate how many people should be vaccinated in order to achieve, we will see in a few minutes, the goal which we want. I will introduce the goal. May I do 50 minutes? 50 minutes is allowed. I do always so because we start more or less 50 minutes later. 50 minutes, just 50 minutes. Let me see about the definition, what I can say. The infection rate, 1 divided time, because as I told you here, on the left part, we have a 1 divided time, number of people with dimensionless with divided time. Here is again dimensionless because it's number of people squared. And of course, just analyzing the unit left equal right, it's clear that this is 1 divided time, typically day. That's the infection rate. Why that? Because as I told you, semiotically, the product states the contact. Mathematically, extremely interesting, but X, Y, they close. Symbolically, they state or reflect, excuse me again, if I am using this word a lot of time with different meaning, the contact between S and I. This is also important math because the symbols, the semiotic aspect, reflect the concept. Contact means product, or the product state the contact. The contact. And R is exactly the rate. No, the rate means, I don't know, in German, what is the word rate? Rate. Rate. Yeah, the infection rate. When they meet, if R is 0, this means, like me, I hope, immune. If R is high, 1, this means 1 contact, 1 infected. It's quite clear. A few things. If the goal is I equals 0, infected equals 0, we can state the error between the number of infected and our goal, desired number of infected. This could be also not necessarily 0, but 0, something which can be nevertheless stated. So set equals 0, we will see typically we don't do, because again, we are aware not all people can be infected. They can be vaccinated. Anyway, goal of infected 0 is reasonable. Why not? This is and typically is not related to the number of people who could be or not could be vaccinated. Why that? I'm not expert on this, probably you can correct me. Look, here we have two inputs. Here we consider just one, vaccination, but I can consider here another input, quarantine. And this is the strongest. We can demonstrate mathematically, but also biologically. If you don't have contact, solution. But of course, this for the society is extremely complicated because no contact means no work, no production, or at least reduction. You remember homework, but in office could be done, but you have working on Volkswagen, and I don't know if homework could be always applied, and then production chain. You have to go there. Of course, you can realize some contactless structure, but extremely complicated. But the quarantine solved the problems. In fact, in China, they applied strong quarantine politics, something like that policy. And they was able to almost without vaccination. Huh? I'm not sure about that. I don't want to say something. I don't want to say something wrong now on YouTube, but it was a little bit more stronger, the policy of quarantine in China with respect to Europe, if I remember well. But please don't disseminate things that is wrong, just in feelings. But mathematically, it makes sense. I told you before, when I told you if there is a wall between rabbit and foxes, we don't have contacts, we don't have, anyway, the rabbits will grow up. And anyway, when we don't have contact, we can understand that we don't have infection. Assuming that no contacts. Mathematically, the parameter 0. And now with the concept that we will close, no? And next week, we will go ahead with the Lyapunov. You'll hear more for math, applicational math, than this concept here, but the idea is also to show you how with this math, with these abstract elements, we can really attack concrete problem, because we will see next week how we can calculate UV to obtain what I equals 0, which is possible too. And now the last concept today, S equal SD. We can see here the error. Do you remember? The concept of the error in control is always clear. Do you remember I told you when I introduced the dynamics of the controller consider the error, which kind of error? What I want to, what I have minus what I want to obtain. This is in the sense of error. And error is not necessarily something wrong. It's the discrepancy. It's in the discrepancy. Look, SD typically, also in practical application, is never 0, because again, not all people can be vaccinated. This defines the immunity. Now look, in the concept of, could be also in a political concept, immunity, a polemic concept. Mathematically, we can state within the value SD after, of course, this comes from the policy from different sources, but the difference between the number of susceptible people and my immunity level, SD is the immunity level. If SD is equal 0, total immunity. The idea is SD as small as possible to control the system at a level of immunity low in this sense. No, you can say high. It depends, but in this sense, if SSD is slow as possible, we have the highest level of the immunity. In fact, it's defined of the maximal number of susceptible people. We have an upper bound. This upper bound should be as small as possible. Okay, next week we will see the second theorem of Lyapunov. This is exactly the topic of our dynamical systems, in which we can see how we can calculate through this second theorem, which allows to fix our equilibrium point. Which is our equilibrium point? S of t equal SD, or around, the concept of around is SD, and I around 0. We will see together using, in the second theorem, how we can constructively, and where we simulate, we will conclude the course with a simulation, which we will see how many people calculate each day, how many people I have to vaccinate. The idea is each day I have to restart with the simulation, because here I am considering a society in which S remain constant. This means no people will born. But of course, between yesterday and today, it could be that somebody will born. But in fact, each day I will restart with the simulation. I will get the information from the health office, I don't know. They know how many people born and so on. And they say, today the susceptible is this. And each day we will simulate what we need for tomorrow. Okay, now I close the lecture, but we will remain a little bit to discuss for possible structure of the last. I hope I was not boring this today. The idea is to show you how we can do a lot of things. Not only to show you the dynamic, the non-linear dynamic, which is important because the reality very often is not, let me say, properly described just the linearity, which is important because it's always the base to think. But we need some more complex structure, which very often we are not able to calculate analytically, but the analytical solution of a linear system can help us to figure out somehow, also in the case, even though these methods or the tools, eigenvalues doesn't work, but we can nevertheless figure out what could happen in a linear system. Okay, I am here to discuss some organization parts, I would like to say. Thank you for your attention. Please don't say that I am against the vaccination, because this YouTube probably will circulate. No, absolutely. But I understand, in accord with what I know, what I also in my experience directly, that there are people which cannot be, or at least is not suggested. So